Hello everyone, we will continue with our lesson today, section 15.10, the second part on change of variables. Now last time we already talked about some building block of this change of variables in triple integrals and in double integrals actually. So I should not say triple integrals here, it's supposed to be multiple integrals. Now, what I plan to do today is I first will give you some examples of how we already use change of variable in the past. You know, like even in calculus 1, we did use substitution, right? So I will try to explain a bit the idea behind Jacobian. And basically, we look back on how we use quote-unquote Jacobian in the past. And then from there, we will apply more how to do this change of variables for problems in our textbook. Okay, I feel that it is not fair if I don't explain to you what this Jacobi actually did. Okay, let me first go back to our calculus 1. So you will see the first half an hour, maybe even up to 1 hour. It's basically review of what we had in the past. So in Calc 1, for example, we have integral. I randomly pick questions here. So let's say we have integrals from 3 to 5 of 2x minus 1 cube dx. Suppose we have something like that. Nobody in their right mind at this point will actually FOIL that 2x minus 1 cube and then integrate term by term. I don't think that's what you want to do. Okay, what we will do instead is we do u substitution, right? Okay, so we use u equals to 2x minus 1 such that our du equals to 2 dx, right? Okay, and at the same time, we will change the limit of integration. When x equals to 3, what will the u be? When x equals to 5, what will the du be? Okay, so now we get integral from 5 to 9. Notice the change in the limits of integrations, right? And then the 2x minus 1 becomes u, right? But what happened to our dx? Our dx becomes 1/2 du, right? We usually just write it as du over 2. Now, and of course, I do expect you to know how to integrate this at this point, right? Now, what I want to point out is that notice that we suddenly have this dx here becomes 1/2 du, right? And this 1/2 is actually our quote-unquote our Jacobian. Okay, if we call this our transformation t, if this is our transformation t, okay, to be more precise, t inverse, right? Then our Jacobian will be, Jacobian for t will be 1/2. Okay, remember Jacobian for t inverse, Jacobian for transformation t is the reciprocal of Jacobian for t inverse, right? Okay, another way to see this, of course, you can see this as u plus 1 over 2 equals to x. That's our transformation t. Okay, now let's go on further, seeing what actually happens in this integration. So originally, our domain of integration is from 3 to 5, right? And then we have a function here. Okay, let's say that's the function 2x minus 1 cube. okay, on xy, is it right? Now, when we do the substitution, then we get the domain becomes u from 5 to 9. Now, I want you to notice that the length of the interval originally was just only 2 units, now becomes 4, right? So this is 2 units here, it becomes 4. So the domain gets larger. But of course, the total area under the curve is supposed to be the same. Now, with that assumption, then, if the domain gets larger, then the height is supposed to be less, right? The height is supposed to be less. Now, if you think about it, then you will see that the height here is actually becomes 1/2 less. Notice, because I already stretched the domain by a factor of 2, right? The domain of the integration, I already stretched that by 2 units. So what happened with the height? Then we actually shrink that by 1/2. Okay, that explains this 1/2. Okay, I hope that that makes sense to you. Now, of course, this kind of explanation is way too oversimplified, because the transformation we have is not only this kind of U substitution transformation. Our substitution may be a trig substitution, inverse trig substitution, and a lot of substitution possible, right? Okay, but at least in this Calc 1 U substitution, I tried to relate to you what we did in the past in Calc 1, actually a very special case of change of variables that we apply in this Calculus 3. Okay, now we also saw in Calc 2 maybe. Suppose we have integral of what is good? Let's say square root of 9 minus x squared dx, right? From 0 to 3. Okay. By the way, if you think about this, this is basically the area of a quarter circle with radius 3. So we know this is supposed to be 1/4 pi 3 squared. That's supposed to be the answer. Okay. Now it's not about the answer. It's about I want to use this example to explain the change of variables and what happened to the domain of integrations and what happened with the Jacobian thingy. Okay, so let's see. Suppose then in Calc 2 we say, oh, you know what? Let's substitute our x to be sine x. As I remember, that's what we did, sine theta, right? So dx becomes cosine theta d theta, right? Okay. Now then, when x equals to 0, what is the theta? The theta is 0. And when x equals to, I'm sorry, it should be 3 here. Yeah, so when the x equals to 3, then the theta will be pi over 2. Okay, so our limits of integration now becomes from 0 to pi over 2. Okay, and square root of 9 minus 9 sine squared theta. And then the dx becomes 3 cosine theta d theta. Okay, now, and then from there you can just compute it, right? Now, again, the issue is not about the computation. I do expect you in Calc 3 to be able to do these simple questions. Okay, what I want to explain is about the domain of integration. Okay, give me a second. So notice that the domain of the integration is, no, not the domain of integration. The domain of integration is from 0 to 3, but the shape of the graph, why I keep on getting this? I want to use this one. The shape of the graph is this here. It's a quarter circle with radius 3, right? Where this is y equals to square root of 9 minus x squared. But if we look at the domain of the newer integration, the integration we have here, notice that the domain now becomes from 0 to pi over 2. Okay, this is the theta. This is 0 to pi over 2. Okay, now then we have this thing here. Let me use red color. We get this thing here, which if we actually clean up, make it nicer, we will get this is 9 cosine squared theta. Okay, you can try simplify that. Okay, and 9 cosine squared theta in the newer rectangular system now becomes something looks like this, I believe. Okay, not precisely the same with that one. No, let me change that. I want to say that it may looks like this. It may looks like this. It may looks like this. I don't know. Okay, but this is the graph of 9 cosine squared theta. Okay, now the thing is, in between how this transformation being happen, how this transformation happen, in between we actually don't know how the x and the y comes into play with the theta and y, and so there's some magic happening between here to here that is something we cannot really explain the way we explain in here. Like the one from in this example one, right? I can say, hey, you know what? You see the domain of integration from 3 to 5 now becomes 5 to 9. Notice that the length being doubled, therefore the height being half, right? But what happened in our next example here, it's not precisely being doubled. It's actually not, it's not being doubled. In fact, if you think about it, it's actually being sectioned this way. It is being sectioned this way. We dissect that this way, okay, and to be like this. To be like this. Okay, so for example, from 0 to pi over 20, that's from 0 to pi over 20, right? So the area we have here is the same to the area we have here, for example. Okay, and the second slice now appears here. Okay, but there's some magic in between how they related. The area is the same, but how that transformation happened from something looks like a pizza into something looks like a rectangle. That's I cannot really explain it in details, but just consider that, hey, you know what, something happened in between and the transformation gives us this thing. Okay, now notice that if we look back to our integration here, notice that this is our Jacobian. Okay, this is our Jacobian. Okay, let's do more. What I'm afraid of doing this is I explain too much of the background. I remember when I taught Calc 3 the first couple times, I get distracted into explaining too much into this and have so little time in teaching, giving you examples from this section. But let's do one more before we do more problems from our textbook. I would like to go over the following example. This is from our previous chapter. Something looks like this. In Calc 3, in the earlier part, we have seen, for example, integral from 0 to 1, and then integral from negative square root of 1 minus x squared to square root of 1 minus x squared. for a function 2 dy dx. Again, our focus is not on how to integrate this. We know how to integrate this. Okay, what we want to see is what is the interpretation, what happened with the transformation, and what is the Jacobian that we had before. Okay, if we think about what this looks like, it's actually the domain of integration is actually a semicircle, right? A semi-disk to be more precise. The x is from 0 to 1. Okay, and the y is from negative square root of 1 minus x squared to square root of 1 minus x squared, and the density is 2, which if we see in 3 dimension, it is actually, you can say this is actually the volume of a prism, with thickness 2. Okay, what is the volume? This is pi over 2 multiplied by 2, so it's supposed to be pi, huh? The answer is supposed to be pi. But again, that's not the issue. The issue is not what is the volume. The issue is when we do transformation, we tend to make it into integral from 0 to, actually from negative pi over 2 to pi over 2 for the theta, and then the radius will be from 0 to 1. The height is 2 r dr d theta. That's how we did it before, right? So this guy becomes this guy. Remember that? Okay, and the domain of integrations, which is originally a semi-disk, half of this, now it becomes a rectangle, right? Okay, now you may wonder, then what is that r? Now that r is actually our Jacobian, if you think about it. Why? Because between rectangular coordinate system to polar coordinate system, we have this transformation x equals to r cosine theta, and the y equals to r sine theta. So when we do the partial respect to r, that's cosine theta, that's sine theta, and partial with respect to theta, that's negative r sine theta, and partial respect to theta here, that is r cosine theta. Okay, now take a look on the Jacobian. This is a transformation t, right? Okay, where the xy coordinate system is ugly, and then r theta becomes nice. Okay, the Jacobian will be cosine theta negative r sine theta sine theta r cosine theta. When we compute this determinant, we get r cosine squared theta minus negative r sine squared theta. That's r times cosine squared theta plus sine squared theta, which is just r. Okay, I hope that explains this r that we have there. Now, originally, when I explained how we do double integral in polar integration, okay, I explained to you that, oh, you know what, the rectangle, a typical rectangle in polar coordinate system is, this is the dr, and this is r d theta, right? Okay, now that is actually a very vague explanation. Okay, a more precise explanation is actually done right now. Okay, now I didn't say that vague explanation is bad, it's wrong. No. It's too much intuition into that. Okay, right now, less intuition, but more systematic. Okay, now if we go on further explaining, okay, then if we try to sketch this integral here, if we try to explain this integral here using theta r coordinate system as if it is a rectangular coordinate system, then you see that the integral is actually from negative pi over 2. I know it's I just put it here, negative pi over 2 to pi over 2. Okay, and then the r is from 0 to 1. Okay, now the thickness, however, if this is theta and this is r, the thickness, the density, however, is 2r. In other words, if I draw it in 3 dimensions, let me try. It's not easy to draw though. If I try to draw it in 3 dimensions, it actually looks like this. The theta is, suppose this is theta. This is theta and this is r. My theta is from negative pi over 2 to pi over 2. The r is from 0 to 1. So the domain of the integration actually looks like this, right? Okay, which is a rectangle. Okay, but the thickness is, the density is actually now 2r, which graphs looks like this. Can you imagine that? So this is the base. That's the base. And this is the height. This is the right wall. Okay, and then this is the front wall. Okay, imagine that. Now, the strange thing is, this is the one maybe surprising for you, is that the volume of this guy here, the volume here, is the same to the volume we have here. The same volume. In other words, when we do change of variables, what happens is we reform, we deform, maybe to be more precise, we change the form of the solid, okay, in a way that is more manageable. Okay, but when we change the form, of course, we need to be very careful. Like, hey, if I stretch the domain by 2, for example, in our example 1 here, then the height should be go down by 2 to compensate that extension, right? Remember, the area here should be the same to the area here, right? Okay, so so suppose I stretch my body, Thomas, I stretch my height to be double, then of course my thickness is supposed to be half. Okay, now that's what actually happened. Okay, I hope this explanation give us a glimpse of what actually happened when we do change of variables. Okay, not only changing of variables give us the Jacobian, but of course we deserve some explanation why the Jacobian looks like that, right? Okay, the full explanation, of course, you can see in the book, but what I do here is try to help you visually see what actually happens. Okay. Actually, if you think about this a bit further, though, what we did in this original integrals, we actually break it up into pizzas, right? A lot of sectors, and those sectors are being reformed into rectangles. Now, however, the thickness of that pizza, let's say we take this one here, the thickness of this a wedge here, this cake here. Now, being like you lie it flat, okay, such that even though the base looks like a rectangle, but the height, let me use this one here. Yeah, the height now becomes the wedge, right? Okay, so imagine the little sections that we have here looks like a cake, if you want to call it that way, right? Now it becomes a triangle sandwich thingy. It looks like this. I hope you can imagine that though. Okay. Now, of course, there are too many things that can happen in between, and instead of like explaining it one by one for each case, Mr. Jacobi help us like, hey, you know what? Let's just do it this way. So he invent this Jacobian determinant to help us. Okay. Now, then, of course, one thing I also need to emphasize here, what happened to the domain of integration. Now, what I'm about to do next is to do some problems from our textbook. Okay, let's start with the ones where our textbook actually give us the transformation. And after that, I will try to explain another way why that transformation makes sense, or to be more precise, do we have other alternative transformation? Let's start with number 16 in our textbook. We have this integral. The integral seems to be simple. The integrand seems to be simple. What is messed up here is the domain. The domain is a parallelogram. Let me try to sketch that first. No, I don't. Let me not do doing this. The domain is a parallelogram. Negative 1, 3, negative 1, 3, 1, negative 3, and then 3, negative 1, and 1, 5. 1, 2, 3, 4, 5. Let's say it looks like this. Now, we don't like this kind of domain though. However nice your domain of your integrand. Okay, so now you notice that we actually have two issues for every integrations. We have issue with the integrand. Is the integrand integrable analytically? But also on the other hand, what happened to our domain? Okay, so what happened is this is our R on XY plane. Okay, so this is our negative 1. I'm sorry, this is negative 1, 3. This is 1, negative 3. This is 3, negative 1. And the one here is 1, 5. Okay, now they tell us to use this transformation. It's very nice of them, which is not true in our real life. 1/4 of u plus v, 1/4 of v minus 3u. Okay, if we use this transformation, notice the transformation actually starting from uv and give us xy. Okay, so this is the t. This is the t. What will the uv look like? It's okay? Let me grab that. Let me grab this and make it a bit smaller. Okay, now let's start with finding the domain of integration in uv. Okay, of course, I need to first find what are these? What are the equations of these segments here? Okay, of course, one thing we can do is actually you do a transformation from coordinate to coordinate. For example, coordinate 1 comma negative 3. Okay, what is the transformation to give us 1 comma negative 3 in xy? What is the u phi? Okay, so 1 equals to 1/4 u plus phi, negative 3 equals to 1/4 of phi minus 3u, and then from there you solve the u for u and phi. You can do that, but if you do that, you basically need to do for each coordinates, at least in each of the vertices here. Okay, that's one way to do. That's one way to do. I will not do it that way though. Okay, in general, that's not what we do. You can do it that way, but that's not what we usually do. Okay, what I think I will do is to take a look at this. What is the equation of, for example, this line here? The slope apparently is 1. So y equals to x minus 4. And this one here is y equals to x plus 4. Okay, and then this line here is y equals to, what is the slope? 2, negative 3, so negative 3x plus 8. And this one here is y equals to negative 3x plus 0. Okay. Now then what happened to these boundaries? That's what we want to do. Okay. So for example, y equals to x minus 4, y equals to x minus 4. When I plug this in, then I get 1/4 phi minus 3u equals to x minus 4. Okay, I can multiply by 4 each term. Phi minus 3u equals to u plus phi minus 16. Put things together. So, the phi cancels, huh? So the phi cancels. Negative 4u equals to negative 16. So u equals to 4. U equals to 4. So basically this line that we have on xy plane being mapped, or the image of that coming from this u equals to 4. Okay. Now how about in y equals to x plus 4? Gedebam gedeboom. I think I will get u equals to negative 4. You can try it. So u equals to negative 4 here. And then how about y equals to x plus 4? That's 1/4 phi minus 3u equals to 1/4 u plus phi plus 4. What am I doing? Oh, I did that one already. My bad, I did that one already. I'm intended to use y equals to negative 3x. So 1/4 phi minus 3u equals to 1/4 u plus phi, is it right? Times negative 3, right? Times negative 3. Multiply by 4 both sides. And then the negative 3u cancels, phi equals to 0. So this line here later on becomes phi equals to 0. Okay? And y equals to negative 3x plus 8 boom multiply by 4. So I will have 1. Let me multiply by 4 right away. So I get phi minus 3u equals to negative 3u plus phi plus 32. Okay, negative 3u cancels. I get 4 phi equals to 32, phi equals to 8. Okay, so notice that then my u is between negative 4 to 4. Very nice rectangle, right? My phi is between 0 to 8. Okay, so later on, when I do my new integral, so double integral over domain R of 4x plus 8y dA, okay, will then becomes double integral over domain D. This is our domain D. This is our domain D in terms of u phi. Okay, then I need to substitute the x and the y in terms of u phi, and then I will have the Jacobian of t, and then I have du dv or dv du. Okay, maybe I call that for now dA in D. This is dA in R. Okay, that's our plan. That's our plan. At least we get the D already. Next, how about the integrand? How about the integrand? So the integrand or the density 4x plus 8y. Now, if I change that in terms of u, that will be 4 times 1/4 of u plus v plus 8 times 1/4 of 3 phi. I'm sorry, phi minus 3u. Yeah, phi minus 3u. Phi minus 3u. This is u plus v plus 2 phi minus 6u. That is, am I right? That will be negative 5u plus 3 phi. Why I feel like something not right? Negative 6. Yeah, that's right. That's right. Okay, that's the integrand. So at this point, the integrand here now becomes 3 phi minus 5u. Okay, how about the Jacobian? We already have x equals to 1/4 u plus 1/4 phi. The y is 1/4 phi minus 3/4 u. So the Jacobian will be 1/4, 1/4, 1/4, negative 3/4. Okay, so that will be negative 3 over 16 minus 1 over 16, that's negative 4 over 16, that's negative 1 over 4. Okay, oh, by the way, the one I insert is actually the absolute of the Jacobian. Okay, so the absolute of that Jacobian of t is 1/4, and that's what I will put in here. Okay, Now, if I put more details, that will be integral from -4 to 4 for the du, from 0 to 8 for the dv, and then 3v minus 5u times 1/4 dv du. Okay, now I believe you can integrate that already. And again, that's not really the issue though. Okay, so that's 1/4 integral -4 to 4 of 3 over 2v squared minus 5uv from 0 to 8 du. So that's 64 divided by 232, 96 minus 40u du. Okay, and then that is equals to that's 96 times 8 minus 0. Okay, so that is what, 192. Again, that's not, it's not about what do it at this point. I believe you should be able to integrate this already from this point and on. Okay, our issue is how do we get from here to here. Okay, that's the one you need to master from this section. So there are 3 parts. First, what happened to the domain of integration. Second, what happened to the integrand of the integration, and what happened to the Jacobian. Okay, now we will discuss later on about this transformation, because of course, what happened if they don't tell us this transformation, we need to figure out ourselves, right? Okay, we will discuss that later on, or should we just do it now? Let's just do it now. Let's just do it now. Suppose I do this question all over again. Okay, but I do not follow, at least I kind of like asking myself, you know what, don't do this. We don't know this. Suppose we don't know this thing. Suppose we don't know this thing. Can I come up with that transformation? Or if we, instead of thinking about can I come up with that transformation, can I come up with any transformations? Okay, so let me copy paste what we have here before. I like this graph, honestly. And I want to say this, take a look at the boundaries, all those boundaries, okay, and change it into something equals constant. For example, this guy here, I will make it x minus y equals to 4. This guy here is x minus y equals to -4. This guy here, 3x plus y equals to 8. And this guy here is 3x plus y equals to 0. Okay, so now I can say, okay, you know what, let my u equals to x minus y and my v to be 3x plus y. Okay, then my u will be from -4 to 4. Oh, well, it seems like we get exactly what we have earlier, huh? 0 to 8. Okay, but notice that this is not the transformation t, this is transformation, inverse transformation t. Okay, now the Jacobian of this t inverse will be 1, -1, 3, 1. You tried it yourself. Okay, you tried yourself. And this will be 1 plus 3, that's equals to 4. Now, what we need is the Jacobian of t, however. Okay, to be more precise, the absolute of Jacobian of t, which is the reciprocal of Jacobian of t inverse. That's how we get that 1/4. Okay, so notice that by doing so, we already have the domain of integration d. We already have the magnitude of Jacobian t. Okay, we still need to deal with the integrand. When we deal with the integrands, let's take a look. Okay, u equals to x minus y, phi equals to 3x plus y. I need 4x, which happens to be the case if I add this, u plus phi. Okay, now how about the y? If I multiply this by 3 and multiply this by negative 1, I get 3u equals to 3x minus 3y. And then negative phi equals to negative 3x minus 3y, which when I add, I will get, no, not negative 3, just negative y, my bad, just negative y. When I add, I get 3u minus phi equals to negative 4y. Okay, I need positive 8y, so multiply by negative 2 will give me 8y equals to 2 phi minus 6u. Okay, so the integrand 4x plus 8y now becomes u plus phi plus 2 phi minus 6u. That gives me 3 phi minus 5u. So we have the ingredients already. The first ingredient, what happened to the domain. The second ingredient, what happened to the the Jacobian, and third one, what happened to the integrand. Okay, now put things together. Double integral over r of 4x plus 8y dA in r is now double integral over d of 3 phi minus 5u times the Jacobian 1/4 dA in r, in d. I take the 1/4 out, 3 phi minus 5u d phi du. The u will be from negative 4 to 4, and the phi will be from 0 to 8. Okay, notice that I did this problem. Oh, by the way, just to make sure that you notice that the setup happens to be exactly the same to what we have here, which is not necessarily true all the time. Okay, yeah, your transformation may be different. Okay, for example, if I change this to be my phi and this is my u, for example, then I get slightly different case, right? But guaranteed that my total final result will be the same. Here, it just happened that my transformation are exactly the same. Okay, my point is, these questions, number 16, the mess up part is the domain. Okay, the integrand seems to be doable actually. Okay, now, so what we need to do is we need to change the domain of integration and make it something nice like a rectangle. But in between of us doing that change of domain, which basically means change of variables, then we need to have some Jacobian to compensate for that kind of change. Okay, now suppose we are not given the transformation. Can you come up to that with that transformation yourself? Okay, now the way I did it here is I look at the boundaries and see what can I do with the boundaries. Basically, I change the boundaries, equation of the boundaries, into an equation with constant on the other side. I think that's the key. I think that's the key. Okay. Now, however, remember that this is the transformation from ugly to nice, right? Now, ugly to nice is the inverse t, not the t itself. Not the t itself. What we need is the Jacobian of t. So, one way to do it is you find the Jacobian of t inverse and then take the reciprocal. Okay? And then the last part is what happened to the integrand. Of course, if you compute this, they happen to be exactly the same to what we have before. So we can guarantee that the final result will be the same. Okay, now let's do more though. You will see we have more and more interesting case. Number 18, for example. You know what? I don't know what the R look like. I'm sorry. I don't know what this R look like. Yeah, I don't know what this R look like. At least that help us with the transformation T. Okay. But again, I don't know what this R look like. I know this is an ellipse. They tell us it's an ellipse. But what that ellipse looks like, I don't know. I don't know. I can try to sketch that though. No, let's ignore that for now. Well, we just know that this R is something ugly, so ugly to the point that I can't even sketch it. Okay, that's an ellipse. Let's say that ellipse looks like something looks like this. That's the R. Okay, now then, what happened to the domain? I don't know what's the domain, honestly. I don't know what's the domain. But let's see the t first. T is x equals to square root of 2 of u minus square root of 2/3 of v. Y is square root of 2 of u plus square root of 2/3 of v. So the Jacobian of t will be, you will see this is square root of 2 minus square root of 2 over square root of 3, square root of 2, and then square root of 2 over square root of 3. That is 2 over radical 3 plus 2 over radical 3. That's 4 over radical 3. Okay. Now then, what happened to the domain? The ellipse R. Should I just substitute them? Okay, so the ellipse, so this is the Jacobian, right? That's one particle. And then what happened to the domain D? So x squared minus xy plus y squared equals to 2. If I do that kind of substitution, I will get square root of 2u minus square root of 2/3 b squared minus square root of 2u minus square root of 2/3 b times square root of 2u plus square root of 2/3 b plus square root of 2u plus square root of 2/3 b being squared equals to 2. Wish me luck. This is 2u squared minus 2 square root of 2 square root of 2/3 uv plus 2 over 3 v squared, and then minus this happens to be difference of squares, so that's minus 2u squared minus 2 over 3 v squared. Okay, plus 2u squared plus 2 square root of 2 square root of 2/3 uv plus 2 over 3 v squared equals to 2. Now I see that this guy cancels with this. That's nice. Okay, this guy cancels with this. Is it right? Okay, the thing is, so we end up with this guy 2u squared plus 2 over 3 phi squared, this guy here, plus 2 over 3 phi squared, this guy here, right? Let me use this. And then the last one, plus 2 over 3 phi squared, is this one here, equals to 2. We'll just move it here. So it's basically 2u squared plus 2 phi squared equals to 2. So u squared plus phi squared equals to 1. Oh, wow. To be honest with you, I will not be able to come up with this transformation, to be honest. No way. No way. I don't even know what domains look like, right? I don't even know what domain look like. So thank God they actually give us the transformation. But we, based on that transformation, we get the Jacobian. We get the new domain D, which is basically now it becomes a disk with radius 1, right? Okay, and then what happened with that what happened with the integrand? Integrand that x squared minus xy plus y squared, which we happen to have done earlier, that gives us u squared plus v squared. Okay, you see the setup is actually so painful, but when it comes to integral, it's actually not that bad. Okay, x squared minus xy plus y squared dA. Now that is equals to double integral over d of u squared plus v squared. And the Jacobian is 4 over radical 3 dA in d. Okay, let me check my Jacobian just in case I make a mistake. Am I good? Okay. So how do we integrate this? Let me pull that 4 over radical 3 out, and notice that the domain D is actually a disk, which I can do another change of variable. I can do another change of variable, 0 to 2 pi, 0 to 1, right? The radius is 1. So u squared plus v squared becomes r, and dA becomes r dr d theta. Okay, it's a rectangular domain and the integrand is independent of theta, so I will just multiply it by 2 pi for the d theta, and then r cubed, when I integrate from 0 to 1, that will be 1/4. So I will get 2 pi over square root of 3 as the answer, or 2 pi radical 3 over 3. The integral is easy to do. To set up this integral is the painful part. Okay, but again, if you ask me this, Thomas, if I give you this question, okay, with this ugly domain, can you come up with the transformation yourself? To be honest with you, my answer is no. The thing is, I don't even know what that ellipse look like though. If I think with my maturity at this point, if they don't tell me this equation as the ellipse, I still know it is an ellipse based on the fact that it's x squared, y squared, right? Okay, and no higher exponent in between. But I still don't know what it looks like though. I know it's an ellipse, but I don't know what kind of ellipse it looks like. Okay. Thomas, will you ask this kind of question in the test where you don't tell us the transformation? No. If I don't tell you the transformation, then the shape should be something you can recognize, like number number 16. Okay, let's go on. Let's go on to more questions. Let's do number 24. This should be the last question I do from this section, and the rest I will do more problems in the supplementary videos. Okay, let's see number 24. Consider this integral over domain R, where the R is a rectangle enclosed by, so it is a rectangle, sounds to be nice until you see what kind of rectangle it is, a painful, ugly one. Okay, so it is a rectangle with x minus y equals to 0. X minus y equals to 0 means y equals to x. So it is y equals to x equals, so it's this one here. X minus y equals to 0. X minus y equals to 2. It looks like this. X minus y equals to 2. X plus y equals to 0. X plus y equals to 0. And x plus y equals to 3. Dang. So we have this R here, huh? Okay. But seems like they implicitly already tell us the good substitution, huh? So our T inverse substitution is U equals to x minus y, and the phi is x plus y. Notice that my U then, my domain D basically then becomes, the U will be from 0 to 2, then the phi will be from 0 to 3. Okay, the Jacobian of T inverse will be 1, negative 1, 1, 1. That's 1 plus 1, that's equals 2. Therefore, the Jacobian of transformation T will be the reciprocal. Remember, what we will use in the integral is the absolute value of that. Okay, so we get the domain D, we get the Jacobian. Now we need what happened to the integrand. Okay, the integrand x plus y e to the x squared minus y squared. X plus y is easy, that's our u, right? But how about e to the x squared minus y squared? By the way, that is actually x plus y, x minus y, is it right, in the exponent? So this is u times e to the u phi. Okay. So now our double integral over domain R, it's a nice it's a rectangle, which is nice, but the shape of the position is so wrong. Okay, x plus y e to the x squared minus y squared. dA is now becomes double integral over d of u e to the u phi. I think we will integrate with respect to what first? Respect to phi first, huh? Oh, don't forget the Jacobian first. That's more important. 1/2, and then this is dA in d. This is integral from 0 to 2, 0 to 3, u e to the u phi times 1/2 d phi du. Okay, now then we need to do some substitution. That's w equals to u phi, so dw equals to u d phi, right? Notice that this is our u d phi, u d phi. Okay, and w for phi equals to 0 is 0. W for phi equals to 3 is 3u. Now this integral becomes integral from 0 to 2, integral from 0 to 3u, and then Okay, so this is e to the w 1/2 dw du. Am I okay now? And from here we just integrate that as usual. That's 1/2 integral from 0 to 2 e to the w from 0 to 3u du. That's 1/2 e to the 3u minus 1 integral from 0 to 2 du. Okay, so this is 1/2 times 1/3 e to the 3u minus u from 0 to 2. E to the 6 minus 2 minus 1/3 minus 0. Okay, so that is 1/6 e to the 6 minus 2, 6, 7 over 6. Okay, painful, huh? Yeah. I need you to practice more though. Okay, so your suggested homework from this 15.10 part B will be from number 15 to 19, 21A, 23 to 27. Okay, I will take a break. We come back in 10 minutes. Okay, let's go on to the next section. If you can come this far, then you must be good. Now, this course is not easy. I know it's a lot. It's quite a steep learning curve for people coming from Calculus 2. But the fact that you pass pre-calculus, you pass Calc 1, and then pass Calc 2, end up being here, unless you came from easy instructors, then you should be proud of yourself that you now in chapter 16 of Calculus 3, which in my opinion, the essence of Calculus 3. Okay, maybe like what I said in my introduction, chapter 12 to chapter 15 is just the introduction introduction to multivariable calculus, and the crown of this course is actually in chapter 16. Okay, of course I'm not saying that chapter 12 to 15 are useless. No, of course there are plenty use of that, right? But we cannot say that you have learned multivariable calculus if you don't touch chapter 16. Okay, now let's start with this chapter. Chapter 16 is on factor calculus. And we will start with section 16.1. 16.1 is a very short section. It's mostly description of what we have in this chapter. We first talk about factor fields. What is factor field? Definition. Let D be a set in R2, in two-dimensional plane. A factor field on that R2, the two-dimensional domain, is not simply a function, but is a factor function. f that assigns each coordinate xy in D a two-dimensional vector fxy. To be more precise, in this case, the vector fxy is actually a vector function. Okay, a vector consists of functions. We usually call the x component function p, and the y component function is function q. Now notice that the function in the x component and the function in the y component both depends on where this coordinate xy located. Okay, so think of it this way: when we say vector field, a vector field, think of that as a field full of vectors. Like for every coordinate you choose on that field, you get a vector. Like, can you imagine paddy field? Right? I come from Indonesia, and Indonesia is a known agricultural country, right? So we see a lot of paddy field where you get the rice from, right? So imagine you have a field, and when we call this paddy field, then any point you choose, there must be a paddy. Okay. Have you ever heard minefield? Now that one is bad, right? A minefield is a field where any point you choose may be something, you have a mine, and then something may be exploding if you stick your foot on any one of the point, right? So think of that, the word fields is like a point, like a region where any point of that region give you, in this case, a factor. Okay. Now, what I give you here is the definition of vector field in 2 dimension. Of course, we can extend this to 3 dimension. So let me write it. Likewise, a vector field on R3 gives the vector function on any given coordinate in 3 dimension is a vector consists of functions for each of the components depends on the position in R3. Okay. Now, for example, I pick easy examples which I happen to see in our textbook so that it helps us in graphing that too. Okay, so for example, we have a vector field fxy given by negative y comma x. Okay, suppose hold on. Suppose, let me change our background to be a coordinate, maybe a bit smaller. Okay, so suppose I have maybe, you know what, change to this one then. So let's say, sorry, I want to move this a bit. I wonder if I can move it. Okay, so For example, when I look at coordinate 1, 0, 1, 0, at 1, 0, the factor will be negative 0, 1. Okay, so at 1, 0, the corresponding factor there is 0, 1. At 2, 0, the corresponding factor there is 0, 2. At this point here, like this. Imagine if this is like a force, then suppose Thomas is standing here, then Thomas will be pushed stronger to the north direction compared to if Thomas standing here. Okay, the force that Thomas experienced at 2, 0 is twice more than the force that Thomas experienced at 1, 0. Okay, they happen to be parallel, but it doesn't have to be like that. How about at f 0, 1? This gives us negative 1, 0, which means at 0, 1, I will be pushed to the left 1 unit. At 0, 2, I will be pushed to the left by 2 units. What happens if we are at, let's say, for example, at 3, negative 3? What happened to us there? 3, negative 3. Then the x component will be equals to negative y. The y component will be equals to x. Okay, so I will be pushed in that direction, much stronger push. Okay, so notice that you can choose any coordinates on this plane here, and for each of that coordinate you choose, there must be a factor associated to that. Okay, and this is one of them. Of course, this is just an example of a vector field, right? What happens if we have a three-dimensional case? Let's say example 2, let vector field f, or sometimes we also call this vector function, xyz equals to ck, or simply 0, 0, z. If we draw it in 3 dimension, okay, notice that it's independent of x and y, So if you are at xy plane, on the xy plane, if you are on the xy plane, the factor is factor 0. X, y, 0, that will be a factor 0. You choose any point on xy plane, it will be a factor with 0 magnitude. However, once you go up a little bit higher, let's say I choose factor, the position 0 to 1. 0 to 1 will be 0 to 1, let's say here. Okay, and therefore the factor associated to that position is 0, 0, 1, which means at that point I will be pushed up by 1 unit. Okay. In fact, that's the case for every x, y, 1. As long as you are 1 unit above the xy plane, then you will be pushed up 1. Okay, even if you are here, let's say, right? still push up 1. If you go even higher, let's say 3, 0, 2, then the factor associated to that will be 0, 0, 2. So the further you are from the XY plane, the stronger the forces pushing you away from XY plane. Oh, with that said, imagine if I go below XY plane, let's say 3, 2, -2. Then the factor associated to that will be 0, 0, -2. Okay, so at this 3, 0, -2, the factor associated to that will be -2. Okay, 0, 0, -2. Okay, again, I hope this enforces, these two examples enforce the concepts that what it means to be vector fields. Basically, you choose any coordinate in R2 or in R3, there will be a vector function associated to that. Okay, now let's move on. Next topic is on something we have learned before called the gradient fields. We learned the word gradient already. Okay, let fxy be given. Let's do three-dimensional xyz be given. Okay, then the gradient of this f is therefore a vector whose x component is the partial of f respect to x, the y component is partial of f respect to y, the z component is partial of f respect to z. Do you remember that? Okay, but the right hand side, as you can see, there's actually a vector whose each component's a function. Okay, now that makes this a vector field, right? Okay, so it's called, now we learned about the gradient. What we want to do right now is to connect to the notion of vector field, and therefore we call this the gradient vector fields. Is the gradient vector field. Of fxyz. Okay. Again, we learned that the idea of gradients already. We just want to emphasize again that the gradient that we learned in previous chapters, I think 2 chapters ago, is in fact the vector fields. One form of vector fields. Okay. Now, next one. Definition. Not related to vector fields. Well, it is related to vector fields. A vector field F, a vector field F is conservative if there is a potential function. There is a function which we will call potential. There's a potential function f such that the gradient of that potential function f is the vector field that we have. Okay, in the next section, I think 16.3 or 16.4, we will learn to find the potential functions. If we have a conservative vector field, then how do we find the potential functions? Okay, now suggested homework from here is given as 16.1, not a lot. This is just number 21 to 25, but try to think a bit. Maybe I tell you which questions that you may want to take a look. To enrich your feeling or your intuition about these vector fields. Give me a second. Number 1 to number 10, maybe number 1 to number 14. Yeah, number 1 to number 14, but the one you need to do is number 21 to 25. Okay. By the way, given this definition, then you see that a gradient field, a gradient vector field, for sure is conservative, right? Because there's a function f such that the gradient equals to that vector field. Therefore, that vector field is conservative. Okay. Yeah, I guess that's what I want to say for now. Okay, let's move on to 16.2. This 16.2 is quite a long section, so that's why I want to cover that right now. Okay, 16.2 is on line integral. Now, while they call this line integrals, it's supposed to be an integral with domain, with curve as the domain. Okay, let's see first. This section will consist of two big parts. The first part is on line integrals of scalar function f. And the second part is line integrals of vector field f. Okay, now what I will cover now is line integral over scalar function f. And if we have a slight time ahead, I will transition to the line integrals of the vector field f. Okay, let's review some part first. Start with line integrals of scalar function f. We start with let C be a curve managed by RT given by xt, yt, zt, where the t is from A to B. You know what? Let's do it in 2 dimensions for now. No difference though, no difference if I make it into 3 dimensions, but for sake of simplicity only. So you imagine that we have a curve in 2 dimensions. This is x, this is y, and the curve looks like this maybe. Okay, where this is t equals to A and this is t equals to B. Okay, and it goes in this direction. Now, in the past, we have learned we have learned the arc length of C of curve C, which is given by S equals to integral over C ds, where the ds is actually the magnitude of r prime t dt. In other words, the arc length that we have before is integral from a to b of magnitude of r prime t dt, right? Okay, where r, if you still need to go further, what is r prime t, Thomas? Well, r prime t is dx dt, dy dt, right? If you have 3 dimension, then another component dc dt, such that the magnitude of that is the square root of dx dt squared plus dy dt squared. Okay, now suppose now if we apply density rho xy on that C, and you can imagine, let's say C is a wire or a cable with different density for each point, right? Then integral over C of density ds is basically the mass of the wire C, right? Okay. Or if z equals to fxy is the surface, then integral over c of f ds is actually the area of the curtain. We sometimes call this lateral area. Imagine the following. Suppose I have this curve on the ground. Suppose I have this curve on the ground here. Okay. And we have surface S such that the curve actually goes up to something like this. Can you imagine this? So this is our z equals to fxy, right? This is the curve C in the domain on the xy plane, right? Okay, so for every point on C that you choose, there's a height associated to it, right? Now then, if you integrate that FDS, what you get is actually the area of this curtain when you take a shower. Like if you do take a shower, then you look at your curtain. From now on, you will remember Thomas and you'll remember this topic. Okay, that's the area of the curtain. Okay, now here I use the C as a two-dimensional curve, but the idea extends to R3. To 3 dimension. Okay, let's do some problem. Here I will do some example. Here I will do some example, and I will just pick questions from the book. Okay, example from the book. It's not really about, you will see it's about the procedure though. Okay, so pay attention on how we set up the integral. Like we are given this integral right now, right? Okay, and how do we compute this depends on how you set it up. Do not rush to the integral without setting it up properly. Believe me on that. Okay, be patient with your setup. Okay. Plenty of times I see students, to be honest with you, not doing well in their later courses because they didn't have a good foundation. They just want to graduate fast, but they take classes from easy instructors and having hard time toward the end of their academic career. Their GPA sucks, and even though they may get the bachelor, but their GPA is too low that they don't have any chance to go on to their graduate studies. You don't want to be in that situation. You don't want to do it so fast such that you basically close all your future doors for improvement. Okay, not a good idea. Okay, not a good idea. Okay, let's take a look on this question. So we have the C is the upper half of the unit circle with radius 1. So it's this one here, right? Okay, that's the upper half. Okay, so let's parameterize that. RT equals to, the regular one is cosine T sine T, right? Okay, so R prime T, long time no see, huh? Is R prime T is negative sine T cosine T. Oh, I forgot the limit of the T. The T will be from 0 to pi. Okay, so the magnitude of R prime T will be gedebam, that's equals to 1, right? Okay, so you will see that integral over C of 2 plus x squared y ds, pay attention to this ds. It's not dr, it's not dx, it's not dy, it's ds. So because we see that ds, we need to find what is ds, which is the magnitude of r prime t dt. Okay, but we know r prime, magnitude of r prime t is 1, so this is basically equals to dt. Okay, now the t will be from 0 to pi, not to 2 pi. 2 plus, now since I changed this in terms of t, right? Since I changed this in terms of t, then all my x and y has to be converted in terms of t as well. This fact should be emphasized even in your calculus too, that once you change the variable of integration into t, then all the integrands has to be in terms of t. Okay? Now, how to compute this? Then it's really go back to your calc 1 or calc 2, right? So this is integral from 0 to pi of 2 dt, which is basically twice the length of the interval, plus integral from 0 to pi of cosine squared t sine t dt. The first term is easy, that's 2 pi. The second term, I need to do u substitution, I believe. U equals to cosine t. So du equals to negative sine t dt. Okay, so this integral becomes 1 to negative 1 u squared negative du. Plus integral from negative 1 to 1 of u squared du. That's 2 pi plus 1/3 u cubed from negative 1 to 1. That's 2/3, huh? 2 pi plus 2/3. Okay, I think the integral part is easy. the integral part is from here and on supposed to be easy part for you, Mickey Mouse. Okay, the one that you need to pay attention is this one. How do you convert from the given integral to you into something that you can work with? Okay, so again, pay attention to the details and the setup. Go on. Maybe I go on with example 3 because I saw it's related, has something to do with that. In example 3, similar, huh? A wire takes a shape of semicircle with radius 1, the upper half, and the thicker near its base than near the top. Okay, so it's basically saying that, hey, you know what, you have a wire with this shape, but then it's thicker near its base than near the top. Okay, now find the center of mass of the wire if the linear density, so the rho at any point is proportional to its distance from line y equals to 1. So if this is y equals to 1, the distance of that, which is 1 minus y, okay, the distance is 1 minus y, proportional, the density is proportional to the distance from line y minus 1. Okay, so k times that distance, which is 1 minus y. Okay, now we want to find the center of mass. Now to find the center of mass, you need the mass, right? And you need you also need the moment with respect to x-axis, moment with respect to y-axis. Okay, and then from there, the x bar will be the moment with respect to y over the mass. The y bar will be the moment with respect to x-axis over the mass. Okay, now the thing is, how do we set up the integration? Well, the mass first is integral over that curve C of rho ds. Got the density ds, right? And how about the path here? This C here is managed by RT equals to, the radius is 1, huh? So we can just use that cosine t, sine t. So r prime t is negative sine t cosine t, where the t is from 0 to pi. So the magnitude of r prime t will be 1. Okay, so the mass will be integral from 0 to pi. The rho is k times 1 minus y, but the y is sine t. Okay, times 1 dt. Okay, this one here is for the r prime t, magnitude of r prime t. Okay, now how to integrate that? That is equals to, that's integral from 0 to pi k dt minus k integral from 0 to pi of sine t dt. Oh, I don't expect this though. Let's see. Oh yeah, this is equals to pi k, and this is equals to 2k. I was thinking it must maybe negative, so k pi minus 2, which is positive. Pi is greater than 2. right? That's the mass. Okay, now how about the moment with respect to the y-axis? Due to the symmetry, I expect it to be 0, but let's take a look. Okay, let's take a look. This is C, and then I insert the x, rho ds, right? Okay, notice that how do we get the moment with respect to the y-axis? Basically, you take the integral you have for mass, and you insert x. Okay, the distance from the y-axis, right? Now I plug in the setup. That's 0 to pi. X becomes cosine t. Rho becomes k times 1 minus sine t, and then 1 dt, right? Okay, so this is equal to I think I can do the u substitution right away. So u equals to 1 minus, oh no, u equals to just sine t. So du equals to cosine t dt. What makes it 0 is that when you plug in u0 is 0 and u pi is also 0, right? Do you see that? So that's k 1 minus u du, but because the limit of integrations are the same, so that's equals to 0. As we expect by symmetry. So x bar equals to 0. How about the moment with respect to x? It's integral. A moment with respect to x-axis, that integral over c of y rho ds. That's integral from 0 to pi. The y is sine t times k 1 minus sine t dt. Okay, so this is k times integral from 0 to pi of sine t dt minus integral from 0 to pi. I don't need to split this actually though. I don't need to split this. However, I happen to know integral from 0 to pi of sine t is equal to 2. Okay, and then for sine squared t from Calc 2, you know you cannot integrate that directly. Right? You need to do power reduction formulas. And when you integrate that, you will see only the 1/2 survive. That's actually minus 1/2 pi. Okay. In other words, what I want to say is like integral from 0 to pi of cosine 2t is equal to 0. How do you know that, Thomas? Well, cosine 2t has period pi, right? Has period pi. So the area under the curve from 0 to pi is actually, they cancel out, right? They cancel out. Okay. So this is equals to, let me do the common factor. So this is 4 minus pi k over 2. So the y bar, therefore, is 4 minus pi times k over 2 divided by k times pi minus 2. At least the k cancels, right? So 4 minus pi over 2 times pi minus 2. Okay, so that's the y bar. That's for example 3. Let's see more. Should I take a look on example 2? Oh yeah, that's right. That's actually a good example. Example 2 is a good example. And I'm glad I actually reorganized the examples here. Now evaluate over curve C, integral over curve C of 2x ds, where C consists of arcs. Okay, C1, parabola y equals to x squared from 0, 0 to 1, 1. So this is our C1, call this C1. Okay, followed by vertical line, 1, 1 to 1, 2. So this is C2. Okay, so basically in the curve C is C1 union C2. Now what I want to emphasize is if therefore later on integral over C is equals to integral over C1 plus integral over C2. Okay, now each with its own parameterization. So in C1, for example, let's call that R1t equals to t comma t squared, where the t is from 0 to 1. And C2 will be the x is constant 1, the y is, you can just call that t, but let me call that 1 plus t, where the t is also from 0 to 1, happen to be. Okay. You can do it this way. You can use just t here. You can just use t here, but then your t will move from 1 to 2. You can also do it that way. Okay, let me just do it that way. Why not? Okay, just don't confuse your t in your R1 and your t in your R2. Okay, now because of this, then what happened to the R prime? R prime 1t will be 1, 2t, whose magnitude is square root of 1 plus 4t squared, while R2t will be 0, 1, therefore the magnitude is simply 1. Okay, now then integral over c of 2x ds is equals to integral over c1 of 2x ds plus integral over c2 of 2x ds. Now, each c1, c2 has its own parameterization. So for c1, the t is from 0 to 1. X will be just 1. The ds is square root of 1 plus 4t squared dt. Okay, plus for c2 will be from 1 to 2. Okay, x is 0. Okay, and then the ds is 1 times dt. Oh, that's equals to 0, huh? So we basically need to integrate this integral from 0 to 1 of 2 times square root of 1 plus 4t squared dt. Okay, now how to integrate that, it's another story that you're supposed to have learned from calculus 1, right? Okay, you're supposed to have learned from calculus 1. Oh, sorry, my x is t. Sorry, my x is t, not 1. So this is t here. My x is t, my bad. Okay, and this is my x is 1. Ah, good thing I check again. I look at this one, supposed to be looking at this one. So this is 1 here. Oh, then it's supposed to be 4 then. It's supposed to be 4 there. Is it 4? What am I doing? No, it's from 1 to 2, so not 4. My bad. It's 2 times the length, which is 1, so it's just 2. Okay, I guess our issue is here. So our u equals to 1 plus 4t squared, so du equals to 8t dt. So dt equals to t dt is du over 8. And u0 is 1, u1 is 5. Therefore, this integral is 2 times integral from 1 to 5 of u to the power of 1/2 du over 8 plus 2. So that's 1/4. Integral of u to the 1/2 is 2/3 u to the power of 3/2 from 1 to 5 plus 2. So that's 1 over 6, 5 radical 5 minus 1 plus 2. Okay. Now that's for example number 2. So I went over example 1, 2, 3 from our textbook. Okay, now let's go on with a slightly stranger one. Not very much that strange, but slightly different. Notice that the variable, the integration we have is always with ds, right? Okay, now let's take a look in the next example here. This is example 4. Notice that the integral we have now is not with ds, but consists of 2 parts with dx and then the dy. Okay, now I will explain later on how this kind of integral is in fact an integral, line integral over vector field. Okay, but let's set it aside for now. Let's see what it means first. Okay, let's take a look on part A. Evaluate this integral where part A is C is C1, the line segment from here to here. So let's do part A first. Part A, C1 is the line segment from -5, -3 to 0, 2. Now, so can you tell what is C1? How C1 is managed? The position is -5, -3, right? And the direction vector is 5, 5. Okay, so it's a 5t, where the t is from 0 to 1. I wonder if you remember this. We did this in the first chapter though. See, the position is -5, -3, right? But how about the direction factor? The direction factor is 0, 2 minus -5, -3. That gives us 5, 5, right? Okay, so that 5, 5, the one give us this. Okay, the position -5, -3 is here. Okay, now then that's R1t. So what is R prime 1t? That will be, well, just 5, 5. Okay. Now notice here they don't ask for ds. What they want is dx dy, which if you think about it, dx dy is basically the differential of dr, right? In this case, okay, which we can now rewrite as dx dt dy dt times dt. Okay, in other words, this is dr dt, which is r prime t dt. Okay, it's r prime t dt without magnitude. Okay, so integral over c1 of y squared dx plus x dy equals to integral from 0 to 1. Now let's take a look. What is the y squared? The y squared will be -3 plus 5t squared dx is 5 dt plus x dy. What is my x? My x is -5 plus 5t times dy. Now our dy is the y component of r prime t multiplied by dt. Okay, now then from here it seems like we can simplify here and there, like common factor 5 dt, and inside we will have 9 minus 30t plus 25t squared minus 5 plus 5t. This is 5 integral from 0 to 1 of 25t squared minus 25t, okay, plus 4 dt. That's 5 times 25 over 3 minus 25 over 2 plus 4. Okay, let's compute this. Common factor 1/6. So 5 over 6, this multiplied by 2, this multiplied by 3, this multiplied by 6. Okay, so that's -1, so that's -5 over 6. Okay, try to picture this. So on the coordinate system, we come from -5, -3 to 0, 2, 0, 2 on the line segment. So that's the line segment from here to here. That's our C1. Okay, now in the second part, we have C2, which is the arc of the parabola x equals to 4 minus y squared. From the same coordinates though, from initial point to the same initial points, the same terminal points, but it is through an arc. Okay, it's through an arc. That's our C2. Now, will that give us the same result? We don't know, okay, but I can tell you it's not, okay? We have some situation where it's independent of the path, but if we don't know that, if we don't know if the situation satisfies, then we cannot say they must be equal. Okay, so we have to compute that though. X equals to 4 minus y squared. X equals to 4 minus y. Actually, I'm sorry. That's not what it looks like. 4 minus x. 4 minus y squared. My bad. It actually looks like this. Let's see too. Yeah, it actually looks like that. Yeah, I somehow think of this as y equals to 4 minus x squared, but then I realized, hey, you know what? If 4 minus x squared is supposed to be 4, right? But then I realized, no, it's not. Okay, so see, one of the key is we still need to find the parameterization for that C2. We are told that the parameter, we get x equals to 1 minus, 4 minus y squared, where x is a function of y, right? Okay, so we can say that our R2T equals to, let's use the y as our parameter, and our x follows from there. Our t, however, will move from -3 to 2. Is it right? Yeah, from -3 to 2. So r prime to t will be -2t comma 1. And integral over c2 of y squared dx plus x dy will therefore integral from -3 to 2. What is y squared dx plus what is x dy? I'm sorry, dx is -2t, huh? This is -2t. I look at the wrong one again. -2t dt, and this is 1 dt. Okay, putting things together, -3 to 2, we get 4 minus t squared minus 2t cubed dt. Okay. You can compute it yourself and compare with your book. Okay, but this is basically the setup. Okay. I think I can just stop here and give you the suggested homework. Please practice though. It gets a lot more difficult from here. Okay. 16.2 part A, number 1 to number 16. And if I were you, I would do all of them while it is still easy. Okay, that's for now.